Alright, so then finally, we try to estimate beta and sigma square jointly. Okay, so then now beta and sigma square are both unknown. Okay, so then this is our original model, right? Okay, sigma square is generated first, and given sigma square, beta is generated, and then given beta and sigma square and x, y is generated from this normal distribution, and then our interest or our goal is to figure out the posterior distribution of beta and sigma square. Okay, so this is our job to do, right? So then to figure out its posterior distribution, what do we have to do? As always, we just try to compute its posterior density using what? Using Bayes rule. And according to the Bayes rule, then this posterior density is proportional to the likelihood and prior. This is our joint prior for beta and sigma square. Prior of beta and sigma square. Then prior of the beta and sigma square's density function is what? Sigma square is realized first, and given sigma squares, then beta is generated. That's why we can decompose the prior of the beta and sigma square. Right? So then now we have three terms: likelihood, prior for beta, prior for sigma square. Now what do you have to do? According to the cases 1 and 2, we should write down the normal density here, and another normal density here, and inverse gamma density here, and then arrange this equation with respect to what? With respect to what? Previously it was either beta or sigma square. Now we have to arrange this equation with respect to beta and sigma square both, right? Yes, of course you can try, but nothing you can do. Nothing. This is something new, something you can't find in any textbook. Okay, so we are done. We cannot estimate beta and sigma square by handwriting. Done. Okay. Then what else you can do? Now we can solve this problem by programming language. We can solve this problem by coding or simulation. Okay, let me explain how to do this. Okay, let me give you the intuition first. Okay, we have no idea what kind of distribution of beta and sigma square. Okay, and at this point, let's remind what we know at this point. What we know is that if sigma square is given, then we know how to generate beta, or we know the distribution of beta given y and sigma square. And we know that beta given y and sigma square it follows normal distribution. If y and beta are given, then we know that sigma square follows an inverse gamma distribution, right? We learned this from what? Case 1. We learned this from case 2, right? And according to this Gibbs sampling method, if we simulate beta and sigma square alternatively and many times, then we can get the samples from the posterior distribution of beta and sigma square given y. So this is the Gibbs sampling, and I don't explain why it works, and you can learn the theoretical background or the proof in the graduate program later, if you want. Okay. So then this is intuition. Okay. I wanna. Okay. What do we want to do, or what do we want to know? We want to know the mean and variance of beta and sigma square. Actually, there is no need to there is no need to know the name of the beta and sigma square given y, right? Right? We don't need its name. What we need is their mean and variance, right? So question is how to compute mean and variance, and keep sampling is the answer. Okay. So then what do I mean by keep sampling? Okay. Here is another intuition. Okay. Suppose you would like to compute the mean of standard normal distribution. And one way is what? You can compute this integral by the definition of what? Definition of expectation, right? So minus infinity and plus infinity. And this is what? This is standard normal density. And then you can compute this by handwriting, right? This is one way, okay? This is one way, okay? Another method is numerical approach. That means suppose you can sample or you can draw the samples from standard normal distribution. Okay, there is basket, and then the basket has infinite number of normal samples. Okay, standard normal samples. So you can draw the samples from the basket as many as you want. Okay, suppose you have 10,000 or 1 million samples from the basket. Then the next thing is you can plot what? Histogram. You can practice histogram, and using the histogram or using just the 1 million samples, you can compute just what? Sample average of the 1 million draws generated from the basket. Then the mean must be what? It's not going to be exactly 1, but it must be very, very close to 0. Okay? This is another way. You can compute the mean of standard normal distribution, right? Only if it's possible to generate or draw the samples from the distribution, right? So then here is intuition. Okay, keep sampling enables us to draw or generate the samples from this posterior distribution. Okay. Then next time I'm going to explain the details about keep sampling. Okay. So anyway, the keep sampling is the key method throughout this semester. Okay. You are going to try the keep sampling so many times. Okay. All right. So then see you next time.